One of the new investigations delivered to the International Space Station by the recent Dragon cargo ship is designed to improve our understanding of the risk of infections that long-duration space travelers face, and it uses roundworms to do the work. Recently, my colleague Brandi Dean spoke with Dr. Cheryl Nickerson, a professor of life sciences with the Biodesign Institute at the Arizona State University, who is the principal investigator of the experiment known as Micro 5.
Cheryl, why don't we start with what we know about how being in space affects an astronaut's immune system? Does it make it easier for them to get sick?
It might. What we do know is that, without question, being in space and in microgravity definitely impacts the crew's immune system. It blunts several aspects of their immune function, so their immune systems don't work as well as they normally do on the ground. We're still trying to learn more of the clinical details as to exactly why it happens, but it's a fact that it does happen. And that's of concern, because even here on Earth, when our immune system doesn't work so well, we're susceptible to a lot of different kinds of diseases, most certainly including infectious diseases. So we are interested in understanding how spaceflight impacts the crew's ability to acquire infectious diseases in flight.
And I understand that meanwhile, being in space can sometimes make the diseases, the microbes, I guess, more virulent. Is that right as well?
Well, we have shown that for one pathogen, and we have shown that for the major bacterial foodborne pathogen in the United States, Salmonella. And that is the only pathogen for which an increased, what we call virulence or disease-causing ability, has actually been demonstrated in flight. However, we've profiled a number of other pathogens in flight, and I can tell you that some of their properties change in a manner which suggests that they might be more problematic to the crew.
Interesting. And I guess that's what your study, Micro 5, looks at, right?
Yes, so Micro5 actually leveraged off of my lab's previous spaceflight research, which was done on the shuttle, wherein we studied the effect of spaceflight or microgravity on microbial pathogens and the infectious disease process. And what's been very exciting to us is we've been able to use the microgravity platform to unveil or reveal new ways that pathogens like Salmonella are actually causing disease in our own bodies. And we are able to use the microgravity platform to get this information, because sometimes when we study these processes on Earth, the force of gravity can mask what the pathogen is doing when it infects us and what our body is doing and it responds to it. So one of the really cool things to us, in addition to having the opportunity to keep the crew healthy in flight, our work is actually translating back down here on Earth with our goal of developing new strategies to help keep us healthy and outpace infectious disease.
Well, tell us a little bit about how this experiment actually works in space.
Sure, I'd be happy to. First of all, the crew in space will set up the cameras so they can do imaging of our experiment. But what they're going to do is they're going to activate the bacteria to grow, Salmonella to grow. Once it's grown, for a certain period of time, they will then infect the nematodes, the host, with that bacterium. And then a portion of that experiment will be put under the video cameras for imaging. We'll get that data in real time. And then other portions of the experiment for gene expression and microscopy will be fixed in chemicals or frozen at different points, at later points in time. And then those samples will be analyzed when they get back. And so I would really like to just quickly mention that it really does take a village to do this experiment. It's been 5 years in the making. We have phenomenal collaborators at every level at NASA. NASA Ames, most certainly, the Johnson Space Center, Kennedy Space Center, the University of Chicago, and oh my goodness, Orion's Quest, who we have high school students there helping us with some of our data and analyze it, but especially to Terry Virts, who has done such a phenomenal job as our amazing crew member who's done this work for us on orbit. We've followed him. We've been so excited. There's no one who could have done it better. And without him, we wouldn't have the work to analyze. So my shout out and thank you to Terry. I'm going to tweet him when I get off this, but he's done a spectacular job. So it's been a lot of work, but a lot of fun.
You mentioned, I think, that you were going to be looking at countermeasures as well for sick astronauts. Can you tell us a little bit more about that?
Sure, I can. I want to kind of preface my comments with saying this is not necessarily a direct countermeasure that would be used immediately, but it could certainly lead us towards one. So our previous work had shown two things. Number one, salmonella became a better pathogen in flight, and on a follow-up experiment, we reasoned we could come up with a way to turn off that increased disease-causing potential in flight, which we were able to do. And we were able to do that with the nutritional countermeasure, which contained several ions or metals like you'd see on the back of your vitamin bottle. One of them was phosphate. And we thought that phosphate actually might be one of the key reasons that we could turn off that increased disease-causing potential in flight. So in this experiment, we're actually in one of our samples, when we infect the nematodes with salmonella, we will have phosphate ions in there. And we will look to see if those phosphate ions can prevent the nematode from getting sick in the first place. If it can, then we've understood something very important about how salmonella causes disease in flight for the crew, and that could potentially be something that could be added to their food as a way, if salmonella actually accidentally got in their food, it missed being detected, to keep them safe. And it could be of direct interest for how to keep food safe down here, because we hear about salmonella recalls all the time, in foods. So maybe if salmonella got into the food, but you had the right level of ions or phosphates in that processed food, you might not have to worry about it. So these are just examples of how we can hopefully help the crew and us be healthier on the ground.
This came up on the latest SpaceX, I think. So when do you think you'll start getting some of the results back to the ground?
So there are three parts of the experiment. The first part of the experiment we're already starting to get back. So the first part of the experiment is real-time profiling of the actual infection process from beginning to end. And the first videos started coming down the very second almost the infection started. Okay, and we're profiling that throughout the course of 14 days. We're getting a lot of real-time data coming down, and we of course have to compare that to our identical ground controls. So we're already getting that part of the experiment down. The other two parts of the experiment have to do with the fact that the astronauts have to freeze or fix the samples for us, and those analyses can only be done back here in our labs at ASU. So one of those is to look at the language that the pathogen and the host are using when they're infecting each other. When the pathogen is infecting the host, because they talk to each other. And I kind of view the infection process as a high-risk poker game, right? You get infected and your body has a response. The pathogen comes back and counters that, and you keep countering one another. And if you have a functional and healthy immune system, you usually win. But you don't always win all the time. And so we want to understand that language between the two of them at a molecular level and at an immune response level. So those kinds of studies will be done on the ground back in my lab. And then we're also going to look inside the worm with microscopes to find out where those pathogens are getting inside the worm in flight and how they differ with where they get when we do the experiment identically on the ground. So we want to put together all of this information to better understand at a mechanistic level why we would see the difference that we hope we'll see in flight with the infection profile, because that would allow us to then take that information and go towards some translational approaches.
Well, it all sounds very interesting. We can't wait to hear how it goes in space and eventually see the results here on the ground. Thanks so much again for joining us. Cheryl Nickerson is the Professor of Life Sciences at the Biodesign Institute at Arizona State University.